Hi everyone, thank you for your interest in our work. My name is Huang, and in this presentation, I will introduce our work, fine-grained talking face generation with video reinterpretation for CGI 2020. So, what is talking face synthesis? It's that give you an audio clip and a face image. Design a system that could produce a sequence of images and further generate a talking face video, and the lip movements should sync with the input speech audio. Basically, there are two strategies of audio to talking face synthesis. Some researchers propose end-to-end models such as distinguishing semantic information from both input audio clips and face image, then directly generating animated face image sequence from the combined semantic features. Usually these kind of methods don't perform well in terms of the speech lip motion consistency. Some researchers divide the training into two stages. They establish a bridge between audio and video by feature landmark prediction. Firstly, they train a prediction network to predict a sequence of facial landmarks. Then use the landmarks and the original face image to generate talking face videos. Although this state-of-the-art approach can generate temporally consistent frames in an audio-driven manner, it lacks direct association between the input audio and final images. Since the output is constrained using predicted landmarks only, and through a single-purpose regression discriminator, the output images can be blurry. The whole quality of each image is insufficiently guaranteed. So our work focuses on improving both video realism and lip motion consistency. The problem will be, how can we design a network that can generate fine-grained talking face videos which not only sync with the input speech, but also maintain the realistic visual details from the input face images. This is the whole strategy. We propose an audio to video to words framework called AVWNet, which exploits the idea of optimizing generation by redescription. The system takes an image of the target face and an audio signal as inputs. The network firstly generates a fine-grained face video in a coarse-to-fine manner. To improve the semantic correlation, the obtained video is then reinterpreted into a vision audio feature space by a lip-reading model, which computes the word's probability distribution through a log softmax layer. The word label with highest probability is expected to align with the ground truth word. At each scale level, we adopt multi-purpose discriminators for adversarial learning. The discriminator for each image frame is conditioned on a speech clip to enhance the semantic association. Based on the corresponding semantic audio clips, our discriminators are trained to distinguish the generated images from ground truth video frames. Furthermore, we apply multi-level attention mechanism and impose it on the internal multi-scale features in our model to weight image features at different levels, so that the generator can precisely rescale and emphasize the dynamic regions. Here V0 is decoded temporal sequential vectors produced by a convolutional recurrent neural network. To simplify the demonstration, we just show one branch of the sequence. So landmark encoder and decoder, the concatenated landmark is transformed to attention nature maps with different size. The subfigure here is the calculation between attention map and latent features. It means that the attention maps focus on the partial movements on the face according to the space, and the other regions that do not move will inherit the features from original facial image to guarantee the person identity. Our proposed network structure consists of a multi-attentional video generation module and a reinterpretive module for predicting the word ID. The video generation process exploits the idea of stack and ++ with multi-state generator and multiform discriminators arranged in a tree-like structures. The generative network receives three kinds of inputs: audio feature, landmark feature, and image feature. Here, A is consecutive time-step audio sequence. Each element A0 to AT represents an inner clip in the audio sequence. They are fed into the audio encoders, and each encoder generates one audio feature A0 to AT. L is a sequence of facial landmarks, and each landmark encoder generates latent landmark features L0 to LT. We take the divergence between the real landmark distribution L and the example landmark distribution L star as one of the condition value. To realize the arbitrary phase video generation, our framework needs to be conditioned on a reference image. Here, I star is an example image. It is randomly chosen from the source frames and transformed into latent variables through an image encoder. Then we concatenate the audio features, example image feature, and the processed landmark features together, forming a hybrid feature each as the condition for the network. Through a conv RNN and two-stage decoders, we can get talking face frames with size of 64 and 128. Semantic video reinterpretation module here maps generated video frames to word space. Here, we adopt a popular lip reading framework. Input the generated videos through a 3D spatial temporal convolutional neural network and a bi-LSTM and a log softmax in the last layer. We can get words probability distribution and realize the word level recognition. Here we use an aggregated per time step loss to align the reinterpreted word and the given audios. D0 and D1 are discriminators in two stages. They take image space clip pairs as their inputs and jointly approximates the conditional and unconditional distributions. They have two training objectives: to distinguish whether the input videos is real or fake, and to classify whether a video-audio fragment condition pair match or not. We use IRW data to train our network, then use LRW and the grid data to test our network. There are 500 different words in LRW datasets. For each word, there are 1,000 videos per speaker. Grid dataset contains 33 speakers, each uttering 1,000 short phrases. We extract the image frames with a sampling rate of 25 fps, which leads to 31 frames for each LRW video and 75 frames for each grid video. All face images are cropped into 128 times 128 by aligning to the landmarks. We train on ground truth landmarks that generated by 2D face alignment library. Our proposed method is evaluated both qualitatively and quantitatively. The quantitative methods we used are SSRM, PSNR, and LMD. SSRM and PSNR aim to assess the quality of our generated videos. LMD calculates the distance between landmarks in generated videos and the ground truth video. It evaluates the audio-video semantic consistency.
With our buddy Shonda Rhimes, but I had to crash this party because today we have been married for 25 years. Now, the idea that you would put up with me for a quarter of a century is a remarkable testament to what a saintly, wonderful, patient person you are. It was a lot easier for me to do it because the fact of the matter is that not only have you been an extraordinary partner, not only have you been a great friend, somebody who could always make me laugh, somebody who would always make sure that.
Here is an example video that showcases our network.
BIM Blue F2 now.
Employers in the country have to say,
what happened,
deal with its financial problems.
Here are some outputs generated by our model on different input phases. Despite the wide variety among input phases, we can see our model effectively synthesizing the lip movements that sync with the input audio.
Happy New Year, everybody. At a time when we turn the page on one year and look ahead to the future, I just wanted to take a minute to thank you for everything you've done to make America stronger these past 8 years.
Liebe Mitbürgerinnen und Mitbürger, ich grüße Sie herzlich. Ich freue mich über die Gelegenheit, Ihnen auch an diesem Silvestertag einige Gedanken zu sagen, die mich an der Schwelle zum neuen Jahr bewegen.
Compared with Chen's model, our model produced sharper talking face with discriminative lips, teeth, eyes, and detailed skin textures. Compared with other methods, the mouth motions also better reflect the input audio.
Just about turns between
The results on the right contain blurry regions and obvious artifacts, for example spots on the face, whereas our approach outputs sharp and detailed videos. We quantitatively compare the performance of our method with state-of-the-art approaches. The higher SSRM and PSNR, the better visual results are. The lower LMD, the better audio-video consistency. For fair comparison, different approaches are evaluated under the same test algorithm and our customized test data size. This table shows that our network outperforms both existing approaches on all three metrics and for both datasets. For user study, we randomly generate 16 talking videos for each method, which are suffered before being shown to 10 participants. To make the survey result more robust, every pair of video is shown to every participant twice. The participants are asked to score on three aspects: the consistency between lip movements and the input audio, the smoothness of the overall video, and the fidelity of each image frames. We compute average scores. The comparison shows that our method outperforms Chen's method in terms of synchronization and image quality. In conclusion, we proposed a fine-grained audio-to-video-to-words network, AVWNet. AVWNet jointly approximates multi-scale conditional and unconditional video distributions and gradually produce videos in a coarse-to-fine manner. We use a reinterpretation module to supervise the generator by remapping the generated video to words again and enforcing the reconstruction loss. Thank you. This is my presentation today. Any questions?